Okay, I'm back. So now we're going to use this top rule up here, or sorry, the second rule here, the case where we have a successor in the subscript and a 0 here. This just turns into n copies of the previous function here. So phi1 of 0 is going to turn into 3 copies of the phi0th function. So let's write that down. So we write down this this whole mess here. So phi0 of phi0 of phi0, phi1 of 0 times 2 plus phi0, and then 3 copies of the phi0th function. Now what is this going to equal here? Let's just take this here and expand that out into phi0 of phi0 of phi0 of 0. Well, we know from the top one here that phi 0 of 0 is just 1. So we'll change that. This is going to equal phi0 of phi0 of 1. And we know that phi0 of a number is omega to the power of that number. So omega to the 1 is just omega. So it's going to equal omega. And then omega to the power of omega, we'll just write that as omega to the omega. So we know that this is going to be omega to the omega on the inside here. So we can rewrite this now. And what I'll do is I'll rewrite this part of the function here. Because this basically over here is going to stay the same for a while until we deconstruct this. This is not going to change it ever. So instead of just rewriting this out for no reason, we'll just deal with this here. So omega to the omega, we can diagonalize, and we know how to diagonalize that. That's something we've done before. This part here is just going to turn into phi sub 0 of omega squared times 2 plus omega times 2 plus 3. And it keeps on going in this fashion, basically. So we can deconstruct ordinals, and they stay on the same line. We don't have to deal with messy exponents and stuff like that. Or if we do, they're very small scale. There's stuff like this. There's not towers of exponents and whatnot. Everything is contained within nested functions. So it's a lot neater way of doing this, and it's it's a much better way of keeping track of where everything is. Okay. So let's do we'll do another more in-depth example, whatever. Let's do. And before I do, actually, I just want to note a little change in notation here. Before, when we plug things into the fast-growing hierarchy, we had f to the a of b. So when we're dealing with Veblen functions and stuff that are going to have very large things in the subscript, we don't want to be hiding monstrosities like this in the subscript when we're writing these things out. So this is going to turn into f a of b, basically. So we can write these things up here, and they're not hiding down here type of thing. So just a slight notational change. A lot of times I'm not even going to bother writing these in the fast-growing hierarchy. I'm just going to diagonalize them like this, just because there's no point in just like putting an f up there for no reason. It's assumed that we can plug these into the fast-growing hierarchy to get really big numbers, but the main point is how to actually deconstruct these things, whatever. It's not necessary that I plug them into here all the time, but so if you see things like this with the square bracket, it just means I'm diagonalizing. I'm showing you the process, but this is assumed to be later plugged into the fast-growing hierarchy to create the values type of thing. So let's do something we didn't do before. We did things like the epsilons and the zetas. So let's say we wanted to do something with the etas. So this would be something like phi sub 3 of something. So let's do phi sub 3 of 1, and we'll diagonalize it at 3. So this is something that if you were to do this the old way, basically doing like f sub eta 1 of 3, it would break apart into some huge, gigantic mess, whatever, and it would get out of hand really, really fast, whatever. So we'll do it with Veblen functions, and we'll show that it's a much neater way of doing things. So what's the first thing we do? This here follows the second rule from the top here. Third rule from the top, sorry. So we have a number in the subscript and then a number in the input basically here. So we do n copies of the previous function here. Then we keep the original function on the inside, minus 1 from the subscript, and then add it to the outside. So let's do that. We're going to take 3 copies of the previous phi function, which in this case is going to be 2. 3 minus 1 is 2. We're going to keep the inside function, so we're going to have phi sub 3 minus 1 from the inside here, so we get 0, and then add to the outside to escape the fixed point trap. This is also diagonalized to 3. Now let's break this apart a little bit. Let's keep 2 copies and then write the third one down. Or whatever. So this is equivalent to writing down phi 2 of 2 of phi of 2. So I want to make that clear that this here so far is the exact same as this. Whatever. I'm just keeping 2 copies and I'm writing the second one down or whatever. Phi sub 3, 0, plus 1. Okay, the next thing I want to do is I want to break apart this one right here. So if you want to think of this now as the inside of this function, we can do this third rule again of making 3 copies of the previous function and keeping the inside function, minusing 1 from the inside and putting it on the outside basically. So now this time, this whole thing is our inside. So we're going to break this part now into 3 copies of the previous function, which is going to be phi sub 1. So let's write that down. So we have this, which doesn't change, phi 2 of 2. Then we're going to have 3 copies of the phi 1 function. Then we're going to keep this whole thing right here, phi sub 2. But now because this is our inside function, we minus 1 from this, so plus 1 minus 1 is just nothing. So we can close this bracket and we add it to the outside to escape the fixed point trap. So here is when you really want to pay attention to where the inside of your functions are. So you know where to minus the ones and add them to escape the fixed point trap. You want to keep a close watch on all your brackets and whatnot to make sure these are going in the right place. So this is the only thing that's a little bit tricky about Veblen functions is keeping track of where everything is going at ever. So again, we'll do the same thing we did here. We'll kind of break apart this 3 into 2 copies of the one function, and we'll break off the last one. So we end up with phi 2 of 2, phi 2 of 1, phi sub 1, phi 2, phi 3 of 0, plus 1, 3 brackets. Okay, so now we want to break apart this here. So now this here is our inside function. So we're going to rewrite this, phi 2 of 2, phi 2 of 1. Break this apart into 3 copies of the phi 0th function. We keep the inside, phi 1, phi 2, phi 3. And we're going to minus 1 from here, so we can close that bracket. And we add it to the outside again. So each time we're kind of pushing this one further and further out. And each time we're doing that, we're escaping a fixed point trap. So again, we'll keep 2 copies of this phi 0th function, and we'll break one off. So phi sub 2 of 2, 2 of 1, 2 of 0, phi sub 0, phi 1, phi 2, phi 3, 0. So now if you recall, phi 0 of anything is omega to the power of that. So if we have this plus 1, we can use this here and turn this into omega to the a times omega. So what we can do is we can get rid of this 1 here. We can close the bracket, and we can go times omega. So that's basically just like applying this rule of exponents right here. Then we can diagonalize this omega. So instead of writing that whole thing just to do one step or whatever, I'll do this here, times 3. Then to work on this further, basically, I want to take, so this 3 applies to this whole thing up to here, basically. So this is this right here. I'll keep 2 copies of this, and I'll add the 3rd copy, so then we can break apart more. So we'll have this from the beginning, 2 of 1, 2 of 0, phi 1, phi 2. Sorry, try not to make this messy, it's difficult. 3, 0, times 2, and then we'll add the last copy of this here. So phi 0, phi 1, phi 2, and phi 3. Now before I write this down or whatever, I want to do a couple steps, kind of, just because it's tedious writing this whole thing down. So we might as well do a couple steps at once. So this phi 3 here now will be able to be diagonalized. So phi 3 of 0, we can follow this rule up here and create n copies of the previous function, basically. So in this case, it would be 3 copies of the phi 2 function. So we're going to do that. Do phi 3 of 2. Now, for the next line, I'll do the same thing as I did before, kind of. All this is going to stay the same for a while. So I'll just rewrite this out. We're going to keep 2 copies of the phi 2 function and break one off. So phi 0, phi 1, phi 2, keep 2 copies, break one off. And the one that we break off is also going to split apart into 3 copies of the previous function, which is going to be phi sub 3 of 1. Rewrite that again. And now we can break apart this into 2 copies of the 1 function. Oops. And end up with phi 1, and that's going to break apart into 3 copies of the phi 0th function. And if you recall phi sub 0 of 0, 3 copies of that turns into omega to the omega, because you have phi 0 of phi, you have phi 0 of phi 0 of phi 0, phi 0 of 0 is 1, omega to the 1 is just omega, and then we have omega to the omega. So you can even just write that on the inside type of thing. Omega to the omega. When we diagonalize this now, we end up with sorry, it takes a while to write out. And also, we'll break this apart. So we'll have, instead of having 2 copies like this, we'll just do them side by side like this. So phi 1, phi 1. And this turns into omega squared times 2 plus omega 2 plus 3. So the same thing that we've done before. And I'll just put dot 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 brackets. So lots of brackets here. And if you want to go further, basically we can treat this as the 3rd rule at the very top here. And do 3 copies of this function. Keep the inside function, minus 1 from here, and put it on the outside. So if you want to imagine like just this part right here would turn into 3 copies of the phi 0th function. Phi 1, you write this down again, plus 2 this time because we're minusing 1 from the inside, and then you add it to the outside basically. And this just continues on in this manner whatever. You can break this apart into 2 copies of the phi 0th function of phi 0, and then use the rule of exponents again to turn this into a times omega, diagonalize that, break it apart, break it apart, break it apart, and it keeps on going like this forever, basically. So, like I said, this explicit example, whatever, of phi sub 3 of 1 would be one of the etas, and if you were to do this out in the old way, it would become very, very difficult, very fast, whatever. So this is a way of keeping everything on the same line or whatever. The only thing really difficult about this is keeping track of where your 1s are going when you're escaping the fixed point trap, and knowing when to diagonalize and stuff like that. But overall, it's a much easier way of doing things, and it's definitely a way to get past this problem where we're having to create an infinite number of letters or whatever. So this is Veblen functions. We're going to do some more examples in the next video. We'll start getting into what happens when we have a limit ordinal in the subscript of the Veblen function. So yeah, that'll be in the next video.